did it. Oh, I don't have the chat going. Okay, I'll look at the chat. He's flustered. We all laughed because Pamela is saying funny things behind the scenes, but he's that's funny. So, but we don't have the guest. Okay, wait, I'm confused now. There's no guest. There's no guest. No, never mind. No, I'll be all right. I'll be okay.
Joy is the guest.
Joy is the guest. What's going on, Moya? Tell me what's happening.
I have been working on my podcast mostly these days. You know, just communicating the science as I do.
Right on.
Mm-hmm.
And how's the video series going?
Oh, it's going really well. Yeah, I'm also have been working on scripts for that. Yesterday, I spent a very long time learning about Aztec mythology, and I think the most important thing I learned was that Aztec wasn't even the word they used to describe themselves. It was a word that a German person came up with to describe them. So if you're talking about Aztecs, call them the Nahua people.
Nahua.
Yeah.
Huh. Okay. Did you see, there was an article I read on, it was on, the conversation somewhere, I forget where I saw it, but someone has taught AI to translate ancient languages.
What?
And so have you heard of linear B, which is sort of like the ancient,
like the old cuneiform?
Yeah. So it's the ancient Greek language, and I think they weren't able to translate it until they got the Rosetta Stone, and then the Rosetta Stone gave enough of a connection to a language that they could translate that they were able. And like a woman spent decades trying to do it, and she died in the 1950s before she had actually completed the project and fully done it. And so they took an AI in 3 hours.
Oh, classic.
Yeah.
There are a bunch of stories like that. I know that there was a group at Harvard trying to decipher knot languages, like writing systems based on tying knots in string, and they were stuck on it for decades until this one undergrad, I think, came in, randomly became interested in it. He had no background in linguistics and then cracked this code.
That's amazing. Couple years. Yeah. And so what's interesting is that because, you know, if you don't know what any character means or any word means, you can't really translate it. But what they did was they looked at how long the characters survived and used that as a way to figure out which characters were most likely and the ones that were beside each other. And they like, instead of like trying to actually go like trying to translate the words themselves, they used all this almost like meta information to get the gist of what everything does. And so they're working with like, you know, all kinds of ancient languages have been completely stuff from India that are just completely people have been working for decades to try and figure this out. And they finally have a way to crack into some of these ancient languages, which is amazing. But not languages.
That's so cool.
Yeah. So finally a good use for AI. Let's turn all those NFT computers into AIs trying to figure out how to translate ancient languages. That'd be all right.
Yes, please.
Yeah. Oh, Zephan says, okay, now do linear A. I don't know. Is linear A a language? I don't.
Yep. Did it come before linear B, or is it like the magnitude system where you work backwards?
I don't know. All right. We've reached the 5-minute mark. So let's get started. Everyone sees a new face, but we'll get into that in a second. All right. Hello and welcome to the Weekly Space Hangout for Wednesday, February 16th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about an upper limit, neutrinos, dead planets crashing into dead stars, how galaxies lose their dark matter, auroras coming from Jupiter, a rogue black hole, and potentially a new type of neutron star. Joining me this week, let's see. We've got Dr. Brian Koberlein. Brian.
Hi. It's been a very long time since I've been here. So
has it?
It's been a while.
Yeah. Do you have any news for us then? Any like television show related news? Any project? There you go.
I can't say anything about any television show, but NRAO has a book out now on the VLA for the 40th anniversary of the VLA.
And did you contribute words to it?
I wrote the words to it.
Right on.
So
how does one get their hands on this?
It will eventually be available on the online gift shop at the VLA.
Oh,
and
amazing.
when they open up to visitors, which they are not open yet, it will be in the VLA gift shop.
And that's in New Mexico.
Yeah.
Yeah. Okay. Yeah. I've been there. It's a crazy place. All right. We've got Dr. Moya McTeer. Moya.
Hi, Fraser. How's it going?
Good. And you? News?
More of the same. Books coming out. Got the
Yeah.
podcast. Cool stuff happening.
Okay.
You should go to the VLA.
I've been there.
Yeah.
I've been.
Okay. Okay.
Yeah. When I was sort of retrieving my wife, then girlfriend, from America, we traveled back, and I made sure that the path we took from Louisiana to the west coast of Canada passed through as many astronomical related things as I could. So we went past the VLA. We went, although we didn't get a chance, it wasn't open, but we went past Meteor Crater. There was a bunch of stuff that we got a chance to see. So yeah, no, it's amazing. It's so cool.
Mm-hmm.
All right. And you might all see a new face today. We got Leah Jenks. Leah, welcome to the Weekly Space Hangout.
Thanks, Fraser. I'm very excited to be here for my first weekly hangout.
So the question I always ask our special guests, but I'm going to ask you, even though you're going to be a co-host from here on out, is who are you and what do you do?
Yeah, so I am a graduate student. I'm almost done with my PhD at Brown University. I work with actually Stefan Alexander, who you all had on here back in December, I think. Mm-hmm. And I work on a really wide variety of things. I'm a theorist, and I think a lot about cosmology and the early universe and gravity and compact objects and some kind of high energy physics as well. So I like to spend my time thinking about all those types of things.
Awesome. And hopefully if you stick around long enough, well, it's almost guaranteed now that you get your PhD. We mint PhDs in this show.
I hope so.
Yeah.
We expect it.
Yeah, it's inevitable at this point. All right. So before we get into this week's news, I want to give a huge thank you and shout out to our good friends at the Weekly Space Hangout crew. Really, they're the executive producers of the show. They choose the guests, they organize the co-hosts, they do everything behind the scenes. Mostly it's Nancy, isn't it? But anyway, but if you want to join this amazing community and give Nancy some help, go to wshcrew.space. You will immediately get your executive producer credentials, and then you can use that to bring on really any guest that you want to see interviewed here on the show. And I think we need more guests, so we should join and become an executive producer and help out, find some cool people to bring onto the show. All right, let's get into this week's news. Brian, finally, we know what the mass of the neutrino isn't.
We know a better upper bound on what the neutrino masses are. So it's one of those weird things. Neutrinos are very strange objects in that one of the things that they can do that most people are familiar with is change flavor. There's 3 different types of neutrinos or flavors of neutrinos. And there's this thing called oscillation, where they can flip back and forth between these different types. And that was what proved to us that they have mass, because if they didn't have mass, they couldn't change their state like that. But what we also know is that there's this weird quantum fuzziness where if you try and measure the mass, then the flavors become uncertain. And they're kind of a superposition of different flavors. Wow. But if you try to measure the flavor, then the masses become uncertain. So you can't say a certain type of neutrino has a certain type of mass. So you can't say the electron neutrino has a particular mass. There's a probability of having one of 3 different masses.
And is this like unsolvable, like the uncertainty principle? Like literally by the laws of nature?
At the same time. In other words, you can't know the flavor of a neutrino and its mass at the same time.
Right.
So yeah, it's kind of like position and momentum in quantum uncertainty.
That's so weird. It would be like saying, how much does that elephant weigh? You mean that giraffe?
Yeah. And it could be a tiny bit, a little bit bigger, or a whole bunch bigger, or it could be a tiny bit, a whole bunch bigger, and a little bit more. And we don't know.
So how did they make... Oh, go ahead, Moya.
Do we know for sure that all the different flavors have different masses?
No, we know there are 3 different masses that oscillate.
Okay.
And there are 3 different flavors of neutrinos, and that's really solid.
Wait. So like when the neutrinos are going through their different flavors, they're changing in mass?
Yes.
Okay. So tell us about the experiment then. How did they figure this out?
The experiment is trying, it's a particle physics experiment. And basically it's getting a stream of neutrinos and trying to determine what that mass cluster would be. And the thing is that neutrino mass measurements have been abysmal. They have been horrible. So they are so bad that even in the past couple of decades, it would be, well, maybe they have negative mass, because the uncertainties on the uncertainty bounds are so huge they overlap 0.
Right.
So we know they have mass, but then what do they have? What is their mass, or what is the mass triplet? Good question. And some of this could be looked at cosmologically. There's been things of looking at like the expansion clustering of the universe to try and pin down that to some degree, but it's very uncertain. This latest one was able to narrow it down that it is no bigger than 0.8 electron volts.
And give me a comparison for something else that is 0.8 electron volts.
So
I guess a 0.8 electron, it's volts.
Well, yeah, I mean, an electron volt is the amount of energy that 1 electron through 1 volt would have. Yeah. So particles are on the order of kiloelectron volts, mega electron volts. This is really small for a particle. And what's important about this is that you can make measurements that can exclude neutrino mass to that level. Because in terms of, go ahead.
Sorry, I was going to ask, is that a bound on all 3 of them, or just on one, or on the combination?
That is, if I understand it correctly, it's a bound on the triplet.
I see.
So the 3 mass.
Right.
Because if you had that, it would fluctuate above it.
And so how did they make this measurement?
Very precise beams. Basically taking particles and watching them decay in a very specific way. And because of the energy, how narrow the energy is of the particles, they can then narrow down what the mass upper limit has to be.
So I guess, how does this have implications for some like, does this have any implications for any other theories out there, like dark matter or early on in the universe? Or
it does. I mean, one thing to keep in mind is neutrinos are a form of dark matter. Mm-hmm. They are the only form of dark matter that we know what the particle is. Now, they're hot dark matter because they're very light and they move very quickly, but they are a form of dark matter. And one of the problems that we have now in cosmology is that, for example, when we measure different parameters for the expansion of the universe, they don't match up in the same way. So if you measure, say, cosmic expansion with supernovas versus galactic area or something, they're just a little bit off. That's what they call tension in the model, because the uncertainties don't quite overlap. So one of the ideas is that neutrino mass might actually bump them into an overlapping area. Right. But we have to know what that mass would be.
Right.
And that's where the problem is. So yeah, it has not just particle physics implications, but also implications for things like cosmology.
And what measurement? This came out of MIT, right? This wasn't done in the Large Hadron Collider. This was there.
No, this was done out of Germany, I think.
Right. Okay. Yeah. The Max Planck Institute, I think, as well, participated in this. So, I mean, is it a very specialized particle accelerator that can do this, or just like
I mean, they're all
experiments done it?
All particle accelerators are specialized. But one of the things that the team wants to do is, now that they've done this, they want to with, I think, a 40-fold or a 50-fold increase in precision. So this is basically, we brought it to this far, and we have ideas on how to take it further.
Yeah.
And that's where it starts to get exciting, because you're getting into the range where, again, you can start excluding theories. Right now it's just, can we even do it? But then if you get even further than that, a factor of 40 or 50, probably start excluding certain theories of neutrinos in terms of their mass.
That's really interesting. Awesome. Thank you so much.
Mm-hmm.
All right, Moya, what do you got for us?
Do you want bright lights on Jupiter or dark matter loss in galaxies?
I want to talk about the dark matter loss in galaxies.
Let's do that then. Okay, so we realized only about 100 years ago that galaxies other than the Milky Way exist, and it's a really interesting history that I don't have time to get into now, but look at the great debate and all of the science and debate that surrounded it. So starting 100 years ago, we understood that galaxies were these gravitationally bound collections of stars and gas and dust. And then when the astronomy community caught on to the existence of dark matter, thanks to Vera Rubin in the 70s, we added dark matter, which is this transparent but gravitationally interacting material. We added that to the list of galaxy ingredients. So for 40 years, the consensus has been that pretty much all galaxies are made of stars, gas, dust, and dark matter, and that the dark matter usually surrounds galaxies in these big blobs of invisible stuff called dark matter halos. And together, all of those halos, all of the dark matter, accounts for about 85% of the matter in the universe. But then in 2018, astronomers found a couple of dwarf galaxies that appeared to have basically no dark matter, and it totally threw a monkey wrench into our understanding of how galaxies form and evolved. Our community was in a tizzy, and we started to rethink what we knew about galaxy formation. And it was especially confusing because we thought up until that point, and we're still pretty sure, that low-mass dwarf galaxies have a higher proportionally a higher dark matter mass content than bigger galaxies like the Milky Way. So dark matter makes up more of their mass.
And sorry, like the controversy comes from, I guess, that dark matter doesn't have a cross section, and so it shouldn't clump in the ways that gas and dust do, and same stars will, can pass through each other. Like if you have all these galactic interactions, it seems really weird that you could just strip the dark matter away from a galaxy.
Yeah, absolutely. Because if they're all interacting gravitationally, why would you expect interactions to take dark matter away, but not the other stuff?
But not the stars, yeah.
So we have been confused about these nearly dark matterless galaxies for a few years now, and a new study that came out on Valentine's Day in Nature from UC Irvine and Pomona, led by my friend Dr. Jorge Moreno, they simulated the evolution of galaxies in a box that was to represent like 60 million light years across. And the simulation, which is this high resolution galaxy simulation, was meant to track the formation, evolution, and collisions of galaxies in the box. And Dr. Moreno has spent a lot of his career focusing on galactic collisions. It was not meant, this is a really important point, this simulation was not meant in any way to reproduce dark matterless galaxies. But it did. So when they ran through the results of the simulation, they had this really cool way of identifying galaxies based on luminosity and density clumping. When they went through all of these galaxies in the simulation, they found 7 little dwarf galaxies that didn't really have any dark matter, that looked a lot like the 2 galaxies we found in 2018. And actually, because Dr. Moreno has this connection to indigenous cultures here in the Americas, the 7 dwarf galaxies from the simulation have all been named after Cherokee clans with permission from Cherokee leaders. So in this picture, you can see that the names are, I think there's a blue and a wolf. And so those are the names of the galaxies.
That's cool.
Yeah. And after synthesizing all of this information, the study found that dark matter gets stripped away from these galaxies through collisions with more massive central galaxies. And it's not that it's just stripping away the dark matter, it's also stripping away stars. This is why you see streams of stars that happen after interactions between central galaxies and their satellites. That's why we have the Sagittarius stream. But because these dwarf galaxies are so small, the luminous matter, the stars, are more clumped, and the dark matter is further away in the halo, and it gets stripped away first. So about 30%, the study predicts that about 30% of the central galaxies in the universe should have at least one dark matter deficient satellite galaxy. So we should have one orbiting the Milky Way. And I just love this because it means that these surprising dwarf galaxies that we found in 2018 that didn't have much dark matter, they aren't actually contrary to our understanding of galaxy formation at all. And if we just dig a little deeper, then we see that it actually really confirms it.
So I'm trying to understand this mechanism. Like, you know, you've got galaxies colliding, the galaxies are passing, their dark matter halos are interacting with each other, the stars themselves are interacting.
Mm-hmm.
But I guess, and somehow these dwarf galaxies are just getting their dark matter stripped out of them, but they're still passing through the collision in some way, or is it on the outskirts? Like, is it like a really special kind of direction that they have to come in to not get consumed by the larger galaxy, but to get their dark matter stripped out?
Yeah, so I think that they would need to comb through the simulation and also see observationally more instances of this out in actual space. But the way that I understand it is that a lot of interactions, these minor mergers, not even mergers necessarily between big, massive galaxies and small dwarf galaxies, is that they tend not to be very just like a straight on collision. It tends to be glancing, where the satellite galaxy is going to be in orbit around the bigger galaxy, kind of like a tiny ball rolling around the edge of a big one.
Right.
And because they're these glancing interactions and not the big, strong collisions where the small one actually moves through the bigger galaxy, then it's just the stuff on the outside, or it's mostly the stuff on the outside that's getting stripped away.
Right. I can kind of imagine, I guess, as the dwarf galaxy is getting closer to the larger galaxy, the dark matter halos are overlapping sooner than the stars are getting attacked by the dark matter by the gravity.
Right.
Leah, do you have any opinions on this?
Well, I have a very naive question, which is, my question is, if you have this two galaxies that are interacting, like, why would the full dwarf galaxy not get like eaten, like we're saying, by the main galaxy? Because I know I've seen that in the context of like the Gaia satellite, looking at like the Gaia sausage and Enceladus and all of those streams. So I'm curious about that.
Oh, I love the Gaia sausage. So I know that minor mergers and interactions between galaxies where there's a really big mass difference actually tend to take longer than interactions where the masses are more similar. And when you think back to like the basics of physics about equal and opposite reactions, that kind of makes sense, because if the mass difference between the two is so big, then the force that the smaller one is enacting on the bigger one is much smaller. So they have these longer scale dynamical interactions.
Really interesting. All right, Leah, you saw them go ahead of you. Your turn. Let's talk about a rogue black hole.
All right, I'm super excited about this story. I think this is so cool. So basically, this is a paper that was posted on the archive a couple weeks ago. It's still under peer review, but it was led by scientists at the Space Telescope Science Institute in Baltimore. And basically, this team has observed for the first time a lone solar mass black hole. And so you might think, well, we've like seen a black hole from the Event Horizon Telescope. We see black holes from gravitational wave detections. Why is this interesting? And the main thing that's exciting here is that, so with like the Event Horizon Telescope, that's a supermassive black hole at the center of a galaxy. LIGO observations are looking at black hole mergers, so there's going to be two of them there. But there are a lot of black holes in the universe that come from stellar death and supernova explosions that are by themselves, and they're kind of on the order of 10, on the order of like 1 to 10 tens of solar masses, and they're just kind of floating through the galaxy by themselves, not doing anything. And of course, these are really hard to detect because black holes don't interact. They don't emit any light. They only really can be seen gravitationally. And so this is very exciting because this team, using 6 years of data from the Hubble Space Telescope, was able to actually observe one of these lone black holes. And so we can see this here. They use a technique called microlensing. So one of the things about black holes is that they warp space-time. Yes, you can see in this little image here. So they warp space-time itself so that light bends. And so what happens is if we have a star and some black hole or some massive object is passing in front of the star, the light gets deflected and kind of focuses like a lensing effect. And that makes the star look brighter when we're observing it. So even though we're not seeing the black hole, we're seeing the star that we're looking at just kind of fortuitously appear brighter. And so this team looked at 8 different objects, and they now have enough data to claim that one of them is a black hole. So they started, I believe, in 2011. And they looked at a progression over, 6 years until 2017. And so they saw this object get brighter, and then they saw it kind of go back to its usual magnitude. So you can see that here. So the August 2011, you can see this one here on the left with the arrow is a lot brighter, and then it kind of dims back down. So that's when the black hole is passing in front.
So I know with gravitational microlensing, like it's mostly used to discover exoplanets so far.
Mm-hmm.
It's been used to discover rogue planets in the Milky Way, but you get like one shot at it. You just get this moment where the star that's in your field of view brightens because it's getting this lensing effect. And if you're lucky, you can detect the planets around it. And then the lensing is over, and then the star dims back down, and then that's it. Is it the same situation with this black hole? They only get one chance to see it pass in front of a star. Is there any way to keep watching it beyond this lensing event?
Yeah, so I think in this case, it is kind of the same thing where there is just like one shot at it. So we can like see here in like 2011, it got really bright. And then basically it kind of just passed on its way and is, going to go in front of some different star. But I think it's not going to be like orbiting the star or anything where we would see some kind of periodic brightening, unfortunately.
And so what were they able to learn about the black hole through this lensing event?
Yeah, so they were able to figure out the mass of the black hole. So they were able to say that it's about 7 solar masses. So it's solidly in the black hole mass range. So it's not a neutron star or a white dwarf. So they did, by that metric confirm that it is actually a black hole observation. But the other really interesting thing is that they used ground-based observations as well. And I think as well as observations from the Gaia satellite to look at, they were able to determine the speed of the black hole in this kind of field. And what they determined is that the black hole is actually moving significantly faster than the other stars nearby, which gives us some insight into supernova collapse and formation, and kind of indicates that when a star is having a supernova event and then turns into a black hole like this, you get an extra kind of like velocity kick, they called it, which I guess in the supernova community, this has been kind of pretty hotly debated as to whether this happens or not. And so this kind of indicates to us maybe because this black hole is moving faster than the other stars nearby, that this kind of kick does actually happen.
Do we know how far away it is?
Yes, we do. I think it was about 1.5 kiloparsecs.
So about 5,000 light years away.
I believe so, yeah.
Yeah. That's close. I mean, it's not close, but it's
yeah, it's in the neighborhood though.
Yeah. Like I think is that our closest black hole? No,
I don't think so.
Yeah. I'm trying to think of like what Cygnus X1 is or something, right? trying to think what our closest black hole is. I should know this. All right. But still, that's kind of cool. So does this, I mean, this was an amazing opportunity. Are there any way that we could sort of try to detect more of them like this?
Yeah, so this team had been looking at 8 total objects. And so this was the first one that they felt they had enough data to confidently say this is a black hole. They kind of tease in their paper that they're going to be releasing results about some of the other objects that they were looking at as well. And I think another big takeaway is that these techniques that they use, this kind of microlensing, looking for microlensing without any like secondary light object, can be used going forward to hopefully find more of these events and be able to learn something, more about black holes and supernova.
Fascinating. Very cool. All right. We'll go around the horn. Brian, back to you.
Okay. So I guess the next one is on being able to see how some planets end around dead stars.
Right.
So we know with the sun, it's going to die. It's going to become a red giant, and it's going to take Earth with it in some form. But one of the interesting questions has been, okay, but in what form? One idea is that as the sun becomes a red giant, the Earth will be thrown out of its orbit. It'll go into deep space. Another one is that it just gets kind of consumed by the star itself, becomes part of the star. But another idea is that maybe it could be put off into a chaotic orbit or fragmented by tidal forces so that it's destroyed in pieces.
None of these sound great.
Yeah,
I don't want any of them.
It's going to be about 5 billion years.
Is the one where the Earth slowly and gently moves away from the sun as it expands into a red giant, always staying inside the habitable zone, and then drifting back inside and going into a permanent orbit as the white dwarf cools down to the background temperature of the universe, giving us another few trillion years of existence in the universe? Is that one of the options?
Sure, why not? But this study says no.
Okay. All right.
So this study looked at white dwarfs, and one of the things about a white dwarf is that it is the core remnant of, say, a sun-sized star or smaller. Basically, they enter a red giant stage. The outer layer gets pushed away from the last minute trying to fuse, and then what's left is something that can't create any fusion energy. It collapses on itself until the pressure of the electrons holds it from collapsing. It's what beats gravity in the end, up to 1.4 solar masses, or the Chandrasekhar limit. So we think of this as just like this kind of hot shell of electron pressure, but it's actually more complicated. It's got elements in it, but most of the elements should be that are on the surface, specifically this kind of thin layer that we call the atmosphere.
The atmosphere.
Well, I mean, it is in a gaseous plasma state. It's just not an atmosphere like what we would think. But it should have elements like carbon, nitrogen, oxygen, because that's kind of one of the common things that you would see, and they are not things like iron or silicon that would tend to be more in the interior of the white dwarf. And so if you look at the atmosphere spectra, you look at the spectra of light coming off of white dwarfs, you can identify the elements in the atmosphere, and in about half of them you find heavier elements. You find traces of iron or silicon, and given the way a white dwarf forms, they shouldn't be there.
Right.
And so one of the common ideas has been, well, probably some material that was in that stellar system collided with the white dwarf after the white dwarf formed. So that if you had, for example, fragments of an Earth-like planet with a nice iron core, it would collide with the white dwarf, and that iron would then be in the atmosphere in the upper layer of the white dwarf, where we can identify it.
Right.
And so it's a great idea. The only problem is that we've never seen things collide that way. We've never seen this type of collision. So was it just a gradual acclimation or whatever? So this latest study looked at using the Chandra X-ray telescope, looked at a particular white dwarf, and what was the name of it? The name of it was G29-38.
It's a beautiful name.
Yeah.
It's a great little name. So they looked at for X-ray flares coming off of the surface. And what they found was they not only observed X-ray flares, but the spectrum of them were matching the right kind of temperature that you would see, which would be, when this material collides with the white dwarf surface, it should be on the order of 100,000 to 1,000,000 Kelvin. And that was there. But the even more interesting one is that the rate at which they were seeing these X-ray flares when this material would hit is consistent with the amount of heavy elements like iron and silicon that we see in the atmospheres. So in other words, the rate at which we're seeing this material accrete on the surface of this white dwarf is consistent with the amount of iron and such that's in the atmosphere of a white dwarf. So,
and when you say accrete, when you use in these very kind of like technical terms, you're talking about just mashed up planets, pulverized.
White dwarf planet bit goes boom.
Right. Ouch. And that's the future of our planet. So what would draw the planet back in to the white dwarf?
Probably when you're still going to have some outer layer material of the nebula, and that's going to cause a certain type of drag. So you're probably getting degrading orbits. You have to keep in mind that during the red giant stage, it's very tenuous. It's not a thick. We would consider it a vacuum on Earth. It's so thin that outer layer is so thin that it's basically vacuum. But it's enough to drag your orbit and cause it to degrade like a Starlink satellite,
Right.
So it eventually comes in, and when it gets closer to the white dwarf, tidal forces are going to break things apart. And so you would have fragments of planetary bodies colliding with this white dwarf.
Right. And so they would be like, they'd cross the Roche limit. They get pulverized into the secretion disk, and then the pieces would interact with each other and kick them down into the white dwarf itself.
Exactly.
Bit by bit.
Exactly.
Yeah.
So the happy ending for Earth of being always in the habitable zone in this model doesn't work.
Right. Because you've still got this material left over after the death that's going to cause this constant drag back in.
Right. You have enough to drag it closer to the star and then, of course, fragment it.
Because hadn't there been planets discovered in the habitable zone of a white dwarf? I feel like, or there have been planets discovered around white dwarfs.
There have been planets found around white dwarfs.
Yeah, yes. They're in the habitable zone, but still.
Yeah, the habitable zone for a white dwarf is it's
very small.
Very small.
Is right. It's
The transits for planets around white dwarfs are basically like just a V, because they cover the whole thing.
Well, Pamela's saying that yes, one was found in the habitable zone last week in some publication. So
there you are then.
There you go. Thank you, Pamela.
So yes, you cling to that bit of hope, Fraser.
I will. Are you kidding? Don't you get this feeling, this kind of like, like the Big Rip is sadder than the heat death, because the Big Rip only gives us about 10 billion years, while the heat death gives us like 1 to the power of 100 years, 10 to the power of 100 years. And so there's something just existential about having more future ahead of us than the shorter time.
Also add that in my book, the Milky Way is sadder about the Big Rip than about the heat death, because the Big Rip means that all of its friends get taken away.
Yeah. And so it's horrifying, and it's sooner. So it's not good. And even though obviously, life on Earth really only has about another 500 million years before the sun cooks us all, somehow we kind of, we anthropomorphize somehow. I don't know why, but it's like we have this sort of existential dread about the future. And I'll take the one that gives us a Google years over the one that only gives us 10 billion years, and everything is torn apart at an atomic level. So anyway, but I have hope. our geoengineering will let us bring the Earth safely back into a proper orbit around the white dwarf, and then we can continue on. I'm going to cling to that hope. All right. Thanks, Ryan. Moya, what do you got?
I am going to transport us back to the golden age of boy bands and leg warmers and neon. And I'm talking, of course, about the 1990s, which is when NASA's Ulysses space probe was launched to study the north and south poles of the sun, which hadn't been done before. It took a few trips around the sun, and on one of those, in 1992, it flew past Jupiter. And for some reason that has befuddled scientists since, it didn't detect any X-rays coming off of the planet. This was so confusing because a planet as large as Jupiter that spins that fast produces a very strong magnetic field. And as particles accelerate through that magnetic field, you would expect to see X-rays. And indeed, when the European Space Agency's XMM Newton spacecraft observed Jupiter, it found low-energy X-rays coming from the planet's poles. These lackadaisical X-rays, as I like to call them, came from Jupiter's aurora, which form from interactions between Jupiter's magnetic field and ions coming off of the very volcanically active moon, Io. It's the most volcanically active body in the solar system. So we did see X-rays coming off of Jupiter with XMM Newton. And then when the Juno spacecraft flew by Jupiter in 2016, it observed that electrons from Io, not ions, but electrons from Io also interact with Jupiter's magnetosphere. And this interaction should produce very powerful X-rays, more powerful than the ones made by the interaction of Io's ions with Jupiter's magnetosphere. So what's the deal? Why didn't Ulysses see these X-rays if they should be there? Well, a new study in the journal Nature, I just was combing through Nature this week, reports seeing the brightest X-rays ever spotted on another planet in the solar system coming from Jupiter. And these bright rays were observed with NASA's Nuclear Spectroscopic Telescope Array, also known as NuSTAR. NuSTAR was designed to specifically detect high-energy, very short wavelength X-rays. And now that astronomers have observed that Io's electrons interact with Jupiter's magnetosphere and also observed these really bright X-rays at the planet's poles, they've figured out that Ulysses just wasn't observing in the right wavelength range to see these X-rays.
So they were there, but Ulysses just couldn't see them.
Yeah, exactly. So these bright lights that Ulysses couldn't see are produced by a type of radiation called Bremsstrahlung radiation. It comes from the German word for to break, and that's not break as in destroy, but break as in decelerate, like pump the. So as charged particles, like electrons, pass through a magnetic field, they produce energy. And the faster they're accelerated, the more energy they produce. And like I said before, Jupiter is a giant, like a very strong magnetic field. So it's essentially like a natural particle accelerator that can make these really, really powerful X-rays. I just love this story because it means that scientists were confused for 30 years about Jupiter, which is basically in our cosmic backyard, because they just weren't using the right tool to look at it.
Right, that it was there all along, and they just couldn't see it.
Yeah.
So would Jupiter have these X-ray emissions at all if it wasn't for Io? Because it sounds like it's contributing both the electrons and the ions.
Yeah, that's a great question. I'm sure it would have some X-rays, but no, probably not strong enough that we could see them.
I mean, like Earth has auroras, and like these are tied to the auroras on Jupiter. Right?
Yeah, coming out the poles. So those are the purple blobs you see there.
Right. But it's not coming from the solar wind or coronal mass ejections in the way that it is on Earth when our auroras form.
Right, because it's so much further away that the particles from the solar wind, the charged particles, aren't really interacting that much with Jupiter's magnetosphere.
It's interesting when you think about like this situation, and then you think about, say, the moons that are orbiting Saturn and how they contribute to the rings on Saturn. Like the moons have a much bigger impact on the planets themselves than I think we ever really expected.
Yeah, on the planets and on the other moons too, because it's the tidal forces, the gravitational interactions between all of the moons that make these liquid water sub-oceans under Enceladus and Europa.
Right. And NASA just launched. I don't know if you saw today, NASA's IXPE satellite. Is that the one? Their new X-ray telescope, the one with this really cool kind of folding, has this detector array that kind of folded out like a, I don't know, like a spring kind of. They did first light just today of this new telescope, and so it's
cool.
kind of like Chandra. So
do you know if it's specifically designed for like low energy versus higher energy X-rays?
Yeah, it's like a different. Hold on, I'm gonna let's see the NASA. Yeah, it's the Imaging X-ray Polarimetry Explorer, and it's designed to measure the polarization of cosmic X-rays of black holes, neutron stars, and pulsars. But I don't know what wavelengths it's looking in. But I just love 2 to 8 kilo electron volts.
Okay, that's lower than New Star, which goes up to like 80 kilo electron volts.
Right. Okay. But I love this as an, people were so worried about James Webb, and NASA launched this one just like a couple of weeks before James Webb, and it had a very complicated unfolding arrangement that it had to do in space, and it did it perfectly.
Nice.
And so, I'm like, yeah, if you're worried about James Webb, look at what just unfolded. Of course, then don't think about Lucy, but which still hasn't got its solar panels fully deployed yet.
Is Lucy the space interferometer, or is that
no? Lucy's
Lisa?
The one that's going out to the Trojan belts for Jupiter.
Ooh.
And one of its two solar, so it's got 2 solar panels that were supposed to open up, and one latched, and the other one is didn't, and is sort of flapping around right now. So, and they may not even be able to get it latched in. So,
oh, R.I.P.
Yeah. Pamela says she's not listening. All right. Pamela, just to let everyone know, Pamela doesn't like to think about spacecraft that haven't gotten first light, completed their mission yet, done their work. She just lives in a state of fear and anxiety, and really just denies their existence entirely. Leah, Pamela is I don't know if you know Pamela. She's the co-host of Astronomy Cast, and also is the engineer behind the scenes on this show. All right. Very cool. Moya, thank you so much. All right, Leah, you get to give us our last story of the evening.
All right. So I guess we have a compact object heavy show today.
Yeah.
Because I'm going to talk about a new potential type of a really cool neutron star that was put out a couple weeks ago, end of January, in a Nature paper by a group out of Australia. And so what they found using the Murchison Wide Field Array, which is a radio telescope in Western Australia, I believe, is actually a grad student was looking through the data and saw a radio transient that was had a period of about 20 minutes. And so this is really interesting because in astronomy, when we think about astronomical like transients of like emission that's only there for a little bit, we have supernova, which we can see for a couple days on to months. So those are kind of like long transients, right? And then we also have on the other side like very short transients. So if we think about a pulsar, those are emitting on kind of like millisecond timescales. But there's really very little that we see kind of in that middle range. And especially we have kind of like appearingly like random radio emission in the middle of nowhere. That's always interesting. I know a couple of years ago, there was a lot of discussion about fast radio bursts, FRBs. People were thinking they were aliens. There were all sorts of crazy theories about this. And so this is kind of a similar observation that people aren't really sure what to make of. But we see these authors found that about every 20 minutes for several hours that there would be a burst of highly polarized radio emission from this object. And the fact that the emission is polarized led them to believe that there were really strong magnetic fields also at play here. And so the timescales and the emission led them to believe that this is something called a ultra long period magnetar. So a magnetar is a type of neutron star. So it's a rotating neutron star that also has magnetic fields. So it's like a pulsar with magnetic fields. But they normally are on kind of normal pulsar timescales, millisecond or second kind of rotations. But this, again, the period is about 20 minutes. So it's rotating really slowly, which is very strange. And so these objects, these ultra long period magnetars, have been hypothesized to exist. So they're theoretical objects that do exist in kind of like neutron star theory. But they've never been observed until now, and that's kind of the best guess as to what this object is. They. So
I was going to ask. So, like, I mean, like when a star dies as a supernova and turns into a neutron star, the baby ones are the pulsars because they're spinning tens, hundreds of times a second, and then they slow down over time as they release gravitational waves, and then they just become plain old boring neutron stars.
Mm-hmm.
So how do you get a neutron star to slow down to the point that it's turning once every 20 minutes, but still giving off this amount of energy?
Yeah, so that's a great question. And it is, as far as I can tell, this is really not well understood. It seems like when we think about neutron star theory and pulsars and magnetars, there's kind of a gap that we don't understand really between how we get from a supernova collapse to a neutron star to a pulsar to a magnetar. And getting to the point where a magnetar can emit radio emission and these like fast radio bursts. And so what the authors are thinking is that this the discovery of this type of object kind of fills in some of the gaps there. But in terms of the actual mechanism that makes it slow down so much, I am not sure. And I think that's, as far as I know, that's really not well understood. So,
I mean, even why magnetars is still not understood.
Right.
Like pulsars, it kind of makes a little sense because they're fresh. Like I recall that it's like it might have something to do with the star having a binary companion during its life, and then there's an accretion disk that's left, and as it spins up, it torques up this massive magnetic field that is then interacting with the surrounding environment. I don't know, maybe it acts like a brake or something as it's spinning in some kind of, in the churned up dead planets, some of which, were left over Earth. I guess it's a neutron star, so we're not orbiting around a super large star. But anyway, so then I guess this fills in gaps in the knowledge about what, I mean, this is what's great is that this was predicted and now it was observed. And that's classic science right there.
Yeah, it's very satisfying, especially for me as like a theorist. And people always say, oh, you work on things that no one can ever observe. I think this is a great example of something was predicted, it seemed really unlikely, and they finally actually observed it. So, and I think it would be really interesting to see, going forward, if this is something that this is kind of a rare object, that, there's really not that many that would, maybe tell us more about the kind of formation mechanisms, or if, now with this MWA and the square kilometer array that I think they're building, we'll be able to see more of these types of objects.
And I mean, you said you described it as a new type of neutron star. I mean, is it a magnetar that just moves slowly, or does it behave differently from other neutron stars in other ways as well?
Yeah, so it does behave normally like a magnetar, but it just has this very, very slow period. So that's the characteristic difference there. Instead of, rotating on time scale of milliseconds, it's 20 minutes, which is a pretty shocking difference.
Yeah, that's really interesting. Very cool. All right. Well, we've reached the end of our hour, and so now it's time for my co-host to shamelessly self-promote whatever it is that they're working on. Brian, what are you working on? But beyond a book, I guess you should talk about the book again. But what are you working on, and where can people find out more?
Okay. Well, the book is finished, so it's coming out soon.
You're not working on that anymore.
I'm not working on that anymore. I'm mostly doing writing for NRAO. That's my day job now. So other than that, you can find me on Universe Today when I write articles, and you can always find my website, which is briancoberline.com.
Fantastic. Moya.
Hi, you can find me on Twitter at GoAstroMo. The pinned tweet on my account is the link to pre-order my book. It's an autobiography of the Milky Way, talks about the history and evolution of our galaxy, but from its point of view. It's pretty fun. And I host a podcast called Exolore that uses science to build and analyze fictional worlds. In the latest one, I imagined life on a planet with a thick atmosphere, and my guests were a bat conservationist and a heavy metal music ethnomusicologist. So we have very fun conversations. Yeah.
That's
heavy
really
metal
cool.
bats.
Metal bats. Do you know the launch date for the book?
August 16th, 2022. It's a Tuesday, I think.
Oh, but you're going to be during our hiatus.
Oh no.
Yeah, so maybe
that's okay. After the book comes out, it'll still exist, so I can talk about it in September. Yeah.
Yeah. So you'll be our special guest then in September. So I'm sure Nancy's all over this already anyway.
Probably.
All right, Leah. If people want to find out more about you, where should they go?
Yes. So you can go to my website, which is just leahjenks.com. On Twitter, I'm at Leah G. Jenks. And I'm unfortunately not writing a book, but
yet.
Hopefully someday.
Yeah, you know what? You're the only person who hasn't written a book, so it's inevitable.
Just like getting a PhD, being a host on the Weekly Space Hangout also means you'll write a book.
Yeah. PhD book.
Yeah, PhD book. Yeah, exactly. And what are you working on though?
Yeah, so right now, speaking of PhD, I'm working on writing my dissertation. And doing all of that. That's been my main focus, and starting up a couple new projects on black holes and modified gravity.
Wow, very cool. Awesome. All right. Well, of course, I'm Universe Today on all the things. On Friday, I haven't put this into the calendar yet, but I'm going to be interviewing Chenoa Tremblay from Australia. Speaking of the Murchison Wide Field Array, Chenoa and her team used it to search for technosignatures at the heart of the Milky Way. Spoiler alert, they didn't find anything, but still, it's going to be fun to talk about the Murchison Array. I'm super stoked to talk about this telescope because it's pretty great. All right. So thank you, everyone, for joining us today. Oh, that's on Friday morning, if I didn't say that. Anyway, thank you, everyone, for joining us today. Really appreciate it. Thanks, everyone, watching us on YouTube and on Twitch. Thanks to Nancy for organizing everything behind the scene. Thanks for all the moderators for keeping everything calm and collected. Thanks to my co-hosts, and a special thanks to Leah. Welcome aboard. I hope this wasn't too painful, and I hope that we'll have you back.
Yeah, thank you.
All right. Thanks, everyone, and we'll see you next week.
Bye.